In any case, what's on board for today? Okay, so we're going to continue in chapter 13. We're actually going to hit a bit of 16.2 before we jump into 16.3. You do have that last mind tap of chapter 15 due today by midnight. Okay, Wednesday we're going to continue in chapter 16, and on Thursday you have some mind taps due. Now likely this 16.3 is not going to be part of that, but we're just going to see how far we make it today in class, okay? And Friday, we're going to do some in-class problems on chapter 16. Okay, looking through your feedback sort of in a very fast breeze this morning, the call for videos is on when to make assumptions. And that's not surprising. Trying to decide when to make these assumptions in our ICE table is one of the most challenging things to grasp, and so I will do my best in the next couple of days to make a review video on when you can make these assumptions for solving in ICE tables as we begin to review for exam 2, okay? All right, so any questions before we jump in today? All right. Okay, so I wanted to pick up a bit where we left off, almost as a little bit of a review here. So why don't we take a minute to make our acid-base, conjugate acid-base pair of this particular equation and answer that first question. Which of the following is the stronger acid? Right, the first thing I would do, label each acid, find its conjugate base pair. Label the base, find its conjugate acid pair. And then look at the two, try to find those two acids on our chart to the right. So as our answers continue to stream in here, the majority is correct that the stronger acid is A, H3PO4. So let's see how we got there. Okay, so I'm first going to label my acid as the ammonium ion. Okay, my ammonium ion has then a conjugate acid-base pair with ammonia as the base. Okay. Then I'm also going to have my base as my reactant, this H2PO4 minus. That has its conjugate acid pair in H3PO4. Okay, so now I've labeled my acid and base and their conjugate pairs. And now I want to go looking at the acids. That's what I'm going to choose first because that's what the question was asking me. So I'm looking for the ammonium cation. There they are. And then I'm looking for H3PO4. Okay, so my H3PO4 is the stronger acid in this case. So I'm labeling that strong acid or a stronger acid in this case than the ammonium cation. And then I want to double check that my bases match up. So I'm looking for ammonia. Okay, have my NH3 and then H2PO4. So my ammonia is the stronger base. Okay, that's NH3 versus my weaker base in H2PO4. Okay, so let me then ask this last question here. Which side is favored, products or reactants, at equilibrium? Okay. Which one do we think? Are we confident? Do we have no idea? What does our neighbor think? All right, let's see how we're thinking. We got a majority, but we're not quite as confident as we were about which acid was stronger. Okay, so results are in, and the majority is correct that is reactants are favored at equilibrium because we go from strong to weak. So we're going from the side of the reaction that has the stronger acids and bases to the side that has the weaker acids and bases. Okay. So at equilibrium, my reactants are going to be favored. Okay. Again, I want to be really careful about the way I'm saying that I'm using stronger and weaker versus strong acid, weak acid, okay? Because I am just ranking their strength based on this table, not a strong acid only being those 7 that we have to memorize, okay? Questions there? Are we feeling okay? Yeah, Liza. Okay, so on the exam, will we have access to this table? We're going to have access to one that's similar. It's actually going to have equilibrium constants. And so when we'll get to those later today, and I'll show you the chart that you'll have. It'll be on the practice exam. Okay? So you do not have to memorize the order of acid and base strength. Absolutely not. Okay? If it was given to you, let's say on the final exam, they may give you all of the KAs, okay, so that you can rank them, but you're not required to memorize their order for sure. Okay. Okay, any other questions there? Okay, so we have seen when we were doing our conjugate acid-base work that water can be considered an acid or a base. Okay, and if you go on to take organic chemistry, water gets to do all sorts of fun stuff. Okay, it gets to act as a base all the time, or an acid for that matter. But water also is a weak electrolyte. Okay, and water can conduct electricity. Right, so when we think about the word weak electrolyte, right, we're not supposed to be in water when there's lightning outside. Right? This is because water conducts electricity. That's because it is a weak electrolyte. If it were a non-electrolyte, we could have a water party in a lightning storm. Okay? But let's not do that. Okay? I don't want to hear, Dr. B said we could have a pool party in a lightning storm. Let's not go there. Okay, so what does that mean? Okay, a weak electrolyte means that we're going to have partial dissociation. So if I think about, I'm going to go back to purple. Okay, let's not worry that my blue 2 means something different. So, okay, so if I have, and I'm just using 2 water molecules because that balances the stoichiometry. Okay, so if I have 2 water liquid, okay, that is in equilibrium with the hydronium ion, or H plus, sometimes as we write it. So H3O plus OH minus. Okay. This dissociation has a K associated with it. Okay, and it gets its own special K called KW. It's the same equilibrium constant that we have been dealing with now for several weeks, but water is special and it gets its own subscript W for water. Okay. And if we were to write the KW based on our original rules, right, I would have H3O plus times OH minus. And it would have no denominator because water as a pure liquid does not belong in the equilibrium expression because I have not given you special permission. Right? So I have this KW expression, H3O plus, the concentration of that times the concentration of OH minus. And this KW value is equal to 1.0 times 10 to the minus 14. That is a number you'd like to store in your brain. Okay, it could go on a flashcard. Okay. So this KW is true, I'm going to say at 25 degrees C. Okay, because we can change the K based on the temperature. But this is the KW, equilibrium constant of water at sort of standard temperature. Okay, so what can we actually do with that K? Okay, let's do our friend an ice table. Okay, so I'm just going to say initially we have lots. Okay, because this is bulk water as a liquid. And we would then have 0 of each of our ions. Okay, I would be moving towards the reactants because I have 0 of each of them. So I'm going to do minus a 2x under my water plus x plus x. Okay, when I come down to my equilibrium line, lots minus 2x is still lots. Okay, and water or liquid is not in the equilibrium expression. That's why solids and liquids don't exist in the equilibrium expression, because they are essentially unchanged. All right, this gives me x. This gives me x. All right, so what I would have is Kw equals x squared. I can then solve for x by taking the square root of both sides. Okay, and I would get that the concentration of H3O plus is equal to the concentration of OH minus, which is equal to 1 times 10 to the minus 7. Okay, so at equilibrium, I have equal amounts of hydronium ion and hydroxide ion, and they are both in a concentration of 1 times 10 to the minus 7. Okay, and we're going to see how these numbers become very important when we talk about pH and the pH scale. Okay, but just a couple more terms, right? We have Kw. This is the equilibrium constant for water and water only. Okay, then we're going to get two more special Ks for the next few chapters. Ka, that's the equilibrium constant for acids. Okay, again, seeing a little bit of a trend. The chemists are not super clever in their naming. A for acid, and drum roll, Kb is for bases. Okay, these are specific equilibrium constants, big K, reactants over products, specifically for water, acids, and bases. Okay, they are no different than any other K. We're just giving them like a little piece of flair to tell you that it's water, an acid, or a base. Okay, so these can tell us, okay, the magnitude of these can give us relative, I think I spelled that wrong, acid-base strength. Okay, because if we have a very large K, for example, a very large K means that something can dissociate into its ions in this particular case, and we would have a lot of H3O plus or a lot of OH minus telling us about the strength of the acid or base at any given time. Okay, and the reverse would be true. If we have a really small K, we would know we're not putting a lot of ion into solution, and so we could have a weak base or a weak acid, depending on what molecule we are looking at. Okay. So when we're dealing with acids, okay, we're really focused on the concentration of H3O plus, and when we're looking at bases, we're focused on the concentration of OH minus. And so we want to be able to relate all of these things so that depending on how a problem is worded or what information we're given to start with, we can get ourselves to the right place. Okay, so I'm going to start with H plus. Okay, and I'm going to, it's the same as H3O plus. I'm just going to write it this way to save a little bit of space. Okay, so if I want to relate the concentration of H plus to pH. Okay, I want to be able to relate those two. I could say that pH is equal to minus the log of the H plus concentration. Okay. If I want to go in the reverse, if I have the pH, but I want to know the H plus concentration, okay, the H plus concentration is equal to 10 raised to the negative pH. Okay, that would be second log or inverse log on your calculator. Okay. The negative there is important. You need to take negative the pH in the exponent. Okay. So those two allow me to relate between concentration of H plus and pH. Okay. Let's then go down to the concentration of OH minus. Okay, so if I want to relate the concentration of H plus to the concentration of OH minus, I can use the KW. Okay, if I look back into that first equation that we wrote up here, okay, I have KW equals the concentration of H plus times the concentration of OH minus. So I can relate the two using the KW. Okay, I'm going to continue around my box here to make POH. Okay, so the POH can be found similar to the pH, but now that's minus the log of the OH minus concentration. If I want to take that, again, OH concentration to POH. And if I want to go in the reverse, then my OH concentration is equal to 10 raised to the negative POH. Okay. All right, and lastly, I want to be able to relate pH and POH. Okay. In order to do that, okay, I can do something called the pKw, which I'll tell you what it is in a second, is equal to the pH plus the POH. Okay, pH, the little p there, really means log. Okay, so pH is minus the log of the H plus, POH is minus the log of OH, pKw is the log of the KW. Okay, so that little p is just telling you that it's the log of that value. Okay, and so that equation actually can become 14 is equal to the pH plus the POH. Okay, how are we feeling about our little square there? Okay, there's a lot of information in that wee little square. Okay, but we want to be able to go sort of all around it and see the power of understanding water being a weak electrolyte allows us to get all of those values. Being able to relate H plus concentration to OH minus concentration. Yeah, Luke. Yeah, so H plus, question is where's H? H plus is just a shorthand for H3O plus. Okay, I just got lazy. Okay, and so you'll see it written both ways. Okay, other questions? Okay, so let's do another sentence for us. Okay, so I have here, what makes an acid or a base a base? All right, and what does that mean with respect to the pH scale? Okay, so here I have concentration of H plus. This is sort of a versus, right? Versus the concentration of OH minus, what that means for the pH and what that means for the POH. Okay. So when a solution is neutral, okay, neutral does not mean equilibrium. So be careful about those two words, okay? So neutral means that my concentration of H plus is equal to the concentration of OH minus. Okay? And that would give me a pH of 7. Okay, when the two concentrations of those are equal to one another. And my POH is also 7. Okay? This happens when you get KW and we solved for X. So our concentrations here of both H plus and OH minus are equal to 1 times 10 to the minus 7. We want to kind of refer back to the previous slide. Okay? So when I take negative the log of 1 times 10 to the minus 7, I get 7. So I have 7 as the pH and I have 7 as the POH. Okay, for an acid, my concentration of H plus is going to be greater than my concentration of OH minus. I am then going to have a pH less than 7. Okay, so from approximately 0 up to 7 is going to be my acid conditions. And for my pOH, for an acidic solution, it's greater than 7. Okay. And lastly, for our base here, in a basic solution, the concentration of H plus is less than the concentration of OH minus. Okay, or I have more OH minus than I do H plus. That gives me a pH greater than 7. Okay, and so for bases on the pH scale, that's going to be from 7 up to 14, where my pOH is going to be less than 7. Okay. Any questions there? Okay, so let's on the next slide here. Let's see if we can think about concentration and what that means with respect to acidity. Okay, so let's try this first one. Okay, concentration of H plus or H3O plus in beaker A is 1 times 10 to the minus 5, and in beaker B is 1 times 10 to the minus 4. Okay, which one of those beakers, beaker A or beaker B, is going to be more acidic? Okay, which one's more acidic? How do we know? What are we looking at for something with respect to the concentration of H plus? Okay, we're coming in. All right, so our majority is correct here that B is more acidic, right? Because a higher concentration of H plus is going to be more acidic. Okay. Now, again, question 2 is the same. Which is more acidic? Okay. Still asking, which is more acidic? But this time, we're only given OH minus concentration. So who's more acidic, beaker A or beaker B? Okay, and the majority, again, we have a large majority, also correct here, that A is more acidic because lower OH concentration means something is more acidic. All right, now let's look at it via pH. Okay, let me clear us off again. Okay, which pH tells us that the solution is more acidic? Okay, which pH tells us we're more acidic? Okay, we're coming in fast. All right, so we are correct. The lower the pH, right? The lower the pH, the more acidic. Okay, and lastly, let's look at the pOH. Okay, which is true. We're looking for which one is more acidic on the pOH scale. Okay, we're feeling pretty confident again. I like it when we feel confident. Okay, and so our pOH, we're now looking at the higher pOH. So a higher pOH will be more acidic. Okay, so we could ask this whole series of questions for which is more basic. Okay, in this table, again, I tried to see if your book has one. it seemingly does not, but this has a kind of a nice way of looking at H3O plus or H plus concentration, pH, or POH, and the OH minus concentration, and kind of getting a feel for what those values look like and how you can rank them with respect to their acidity or their basicity if we wanted to go in the reverse direction. Okay. And I kind of want to remind us Kw is equal to H3O plus times OH minus. Okay, these expressions are what allow us to relate them to one another, and that my pKw is equal to the pH plus POH. Okay, so again, that's 14 is equal to pH plus POH. So I can relate them, right? So if my pH is 1, my POH is 13, right? The sum of them have to equal 14, always, because of the Kw. Okay, we feeling all right? Yeah? Okay. The thing I'll also tell you is that as we continue to work these acid-base equilibria problems, we're going to use the skills from just, I'll call it regular equilibrium. Okay? We're not doing some new crazy ice table yet. We'll put that off to buffers in the next chapter. We're not going to worry about that yet. Okay. So our first example here is that we have 2 molar perchloric acid in water. Okay, so perchloric acid is HClO4. Okay, so my question here is perchloric acid a strong acid or a weak acid? Okay, A is strong acid, B is weak acid. Okay, all right, we're coming in here. We had a pretty large majority going, and the majority is correct that perchloric acid is a strong acid. I'm going to remind you that making a flashcard of our 7 strong acids is a very good plan because it can save you a lot of time and effort in the calculation of these problems. Okay? So perchloric acid is a strong acid. Okay? That means that it completely dissociates into its ions. Okay? So I am going to favor products for sure. Okay, so that's HClO4, aqueous, okay, in water, liquid. Okay, I'm going to draw a first down arrow here, okay? If you have a strong acid, you do not have an equilibrium arrow, you have a first down arrow, right? Because everything goes to the products. It's just like a completely soluble salt, okay? If that's true, I'm going to form H3O plus, aqueous, plus ClO4 minus, aqueous. Okay, so that is me completely dissociating into my ions. Okay. If I have a strong acid, okay, my equilibrium is always going to go in the forward direction. Do I need to do an ice table? Do I need one? Okay, if I'm solving for the pH. Okay, see, Matthew, going like this. No, I do not. Okay, so you may be saying, how do I know? Why? Why do I not have to do an ice table? Okay, my pH, right? The pH is equal to minus the log of the H plus concentration. Okay, if I have a strong acid then the concentration of the ion is going to be the initial concentration. Okay, so I can say that the pH is equal to minus the log of 2. That's the concentration given to us in the problem. Okay, so the pH of 2, or sorry, minus the log of 2 gives me a pH of negative 0.301. Okay, and that's why I wrote in the previous slide that it's approximately 0. Very concentrated strong acid can have negative pH. Okay, but that is essentially 0. That is very, very acidic. Okay, so, well, what if I wasn't sure it was a strong acid, or what if I wanted to do an ice table? Well, I'm not going to take, the excitement of an ice table away from you, okay? We could have done an ice table where I started with 2 here, and all of these you're going to see me draw a squiggly in water because it is not part of the equilibrium expression. It does not change, okay? And so I'd have a 0 here and here. I would have a minus x and a plus x. Okay, and so I would have 2 minus x, x, and x. Okay. So if, again, I knew that it was a strong acid, so if a strong acid, right, I know the x is equal to 2. Okay, so I would have the concentration of HClO4 is 2 minus 2, or equal to 0. Again, this is a first down arrow, not an equilibrium arrow. And my concentration of H3O plus is equal to the concentration of ClO4 minus. They're both equal to 2. Okay. I then would take that 2 back up and, again, do the same math that I just did. Log of 2, that's where this 2 comes from. And I get that pH is equal to minus 0.301. Okay. The reason I don't like to do the ice table when I have a strong acid is because it makes me think I need the Ka, or I need to make an assumption, or did I need to use the Y, right? And so I start to spiral into all of the rules for equilibrium that we previously used, okay? And so I kind of like to put a stop on that sort of mind vortex. If I see a strong acid or a strong base, I do not need ice, okay? Maybe I'm making a weird sports analogy. If you're strong, you don't need ice. I mean, everybody, if you need a sore muscle, you need ice, but that's where my brain was just going. Okay? If you're strong, you don't need ice. Okay? It's a little silly. Everybody needs ice. Okay? But that's helping my brain. Okay, questions there? All right, so anytime I am given a concentration of strong acid or base, I can put it right into my pH or pOH expression. Okay, well, I know we're not going to be that lucky all the time. Okay, we're going to have to look at weak acids. Okay, acetic acid is a weak acid. It's a classic weak acid. All right, that's what our vinegar is. And in this case, I'm giving you the pH. Okay, the pH is still acidic between 0 and 7. Okay, so if I wasn't sure if it was an acid, that pH should give me a heads up. Okay, but that pH, again, still acidic, but not crazy acidic. I'm going to tell you that means reactants are favored, and I'm going to prove it to you. Okay, you may not have been able to say, given that information, whether reactants or products are favored, and that's okay. All right, but I'm going to try to prove that to you. Okay, if I just have an initial concentration of something and nothing about the products, I know I'm going to go in the forward direction. And so let's see if we can find these values. Okay. So all I'm given is the concentration of acid and the pH. Okay, I'm going to write the equation first. Okay. If you don't know what acetic acid's molecular formula is, that's okay. You could abbreviate it HA. Okay, H for the H plus, A for the anion. The formula of acetic acid is CH3COOH. Okay, that's what I'm calling HA. That whole thing. Okay, so HA aqueous plus water is in equilibrium because it is not a strong acid. It does not get a first down arrow. All right, with H3O plus aqueous plus A minus. Okay, and A minus is equal to CH3COO minus. Okay. The weak acid HA shorthand can save you a lot of time if you're writing an equation out on the exam. Okay, because frankly, at this point, it doesn't matter what they are. Okay, this is also aqueous. Okay, so I know that this is 2. Okay, I know that these are 0. I know that this is going to subtract. Nobody cares about the water. I'm going to add over here. And I get a 2 minus x, an x, and an x. Okay, well, great. I don't have a Ka. I know that HA at equilibrium is 2 minus x. Okay. But I don't have anything else to plug in. But what am I given up here? Okay, I'm given the pH. And that pH can give us the concentration of H3O plus at equilibrium. Okay, so where does that go, right? So I have my 2.22 is equal to minus the log of the H3O plus concentration. Okay, if I look back at my little box before, rearranging that gives me 10 to the negative 2.22 is equal to the pH. Oh, sorry, that's totally not true. Is equal to the H3O plus concentration. Okay. That gives me 0.006, which is equal to the H3O plus concentration. Okay, so if that pH is measuring the H3O plus at equilibrium, that number is equal to X. Okay. So if I'm equal to X, then I can solve for the Ka. Right? My Ka expression here would be H3O plus times A minus all over HA. So I'm going to substitute in my 0.06. And I have 2 minus 0.006. Okay, when I do this math out, I get 1.82 times 10 to the minus 5. Okay, this is my Ka value. That is a K less than 1. So my reactants are favored. How do we feel about that? Okay. Sometimes I like to always set up the equation, right? I realize that it's not a strong acid, so I need to do an ice table, and then I get down and I'm not sure what to do. I look back to the problem to see what I have. Yeah, Avery. Yeah, so the question is, because acetic acid is not a strong acid, I cannot just use the 2 molarity. The answer to that is yes. Because, so I've given you the pH here, right? The pH of 2 molar perchloric acid was negative 0.3. The pH of a 2 molar acetic acid is 2.2. Okay, so in this particular case, I've already given you the pH. So the question could ask, what's the H plus at equilibrium, and not ask you to do the whole ice table. I only need to do the ice table in this particular case to solve for K. Okay, because I can use the pH to directly get the H plus concentration. Okay, but that's a really important point, that only if you have a strong acid or base can you take the concentration straight into the pH formula. Yeah. Okay, so the question is, I thought if we had a K less than 1 and we were reactants favored, I thought we moved in the reactant direction. That's only if we have starting quantities of everybody and we've solved for the Q. So if I do a Q calculation for this, I would get 0 over 2, right, which is 0. And my Q, I don't know what my K is in this case, but I assume that I have to go forward because I have no reactants at all. Okay? But yeah, that's it. Again, when we're thinking about Q versus K. All right? But if I start with 0 products or 0 reactants, the reaction's always going to go in the direction of the 0. Okay? Okay, so as we wrap up, let's do a base. Okay, so in this case, I'm giving you a weak base. This is ammonia. And I'm giving you the Kb. Okay, so this is the equilibrium constant for the base. This K is less than 1. So at equilibrium, my reactants are favored, but I'm again only given a concentration of the ammonia. So I want to write ammonia plus water is in equilibrium with the ammonium cation. These are all aqueous, by the way. This is liquid. Okay, plus hydroxide. Okay, again, this has a Kb equal to 1.76 times 10 to the minus 5. Okay, if I think about an ice table here, I have an initial 1.5 molar of ammonia. Nobody cares about the liquid water, sorry, buddy. And I have 0 of the others. Okay. Because I have 0, even though my K is very small, I'm going to proceed in the forward direction. All right, so I get a minus X, I get a plus X. So I have 1.5 minus X, and X. So if I substitute those back into the Kb, again, this would be NH4 plus times the concentration of OH minus, all over the concentration of NH3. Okay. If I substitute then in my values from the equilibrium line, I would get X squared over 1.5 minus X. Now I've brought myself to assumption land, okay? We've made it back to sort of where we began in equilibrium. Okay? If my K is very, very small and my concentration initially is reasonably large, I can get rid of that X, assuming that X is very small and that the change of the initial concentration is negligible. So I then get X squared over 1.5 is equal to 1.76 times 10 to the minus 5. I'm going to cross multiply my 1.5, and then I'm going to take the square root to get X. Okay, so X is equal to 0.0051. Okay, this is equal to the concentration of NH4 and the concentration of OH minus. Okay, because those were my X's here. Okay. Now, I cannot go directly to pH because I don't have H plus concentration. Okay. There's a number of ways to get there. Okay, you could use KW, but I'm going to use POH, and then go to pH. Okay? So I'm going to say that POH is equal to minus the log of the OH concentration. So that's minus the log of 0.0051. That gives me a POH of 2.29. Okay? And then I want to say that 14 is equal to the pH plus the POH. So 14 minus 2.29 is going to be equal to the pH, which is equal to 11.71, is equal to the pH. Okay, so I know we got to the end there pretty furiously. We'll make sure we start there on Wednesday. Just kind of walk ourselves back through there. All right, bye.